Hi everyone. Now I'm going to introduce our paper, Easy to Deploy API Extraction by Multi-Level Feature Embedding and Transfer Learning. So what is API? API is a set of definitions of functions or modules for building application software. There are some examples for API libraries, such as NumPy, OpenGL, JDBC. There are also some API methods, such as NumPy.render, getBaseType. So what is API extraction? Distinguish API mentions from general natural language words in API documentation is referred as API extraction. The following is one example. The NDE is annotated in this paragraph because it is an API mention. There is another example for API extraction in formal discussion from Stack Overflow. In this answer, we can say the set state and render are annotated because they are API mentions. And why is this task important? Because API extraction is the prerequisite for many downstream applications, such as document linkage and document-specific question and answering. And why is this task challenging? Well, API mentions in formal software tests usually lack consistent writing forms and annotations. In this example, we can see the apply have lots of different writing forms. Furthermore, an API may have a common word simple name, such as the apply or series. In this example, we can see in the first sentence, the apply is an API mention, but in the second sentence, the apply is just a common word. So we cannot just use the rule-based method to distinguish API mentions. As for the motivations, well, designers of a machine learning-based API extraction model have to manually select the most effective features for different libraries and APIs. Some advanced features to boost API extraction for performance, such as word clusters and API gathers, have to be handcrafted. So we are motivated to design a neural architecture for API extraction in formal software test. As for the contributions, our work is first to consider not only the performance of machine learning-based API extraction methods, but also the easy deployment of such methods. And we propose a multi-layer neural net architecture to automatically learn to extract the effective features from the input test for API extraction. And we adopt transfer learning to reduce the overhead of manual labeling of the training data of a subject library. And we conduct extensive experiments to evaluate our architecture as a whole, as well as its components. As for the dataset, we selected 3,600 Stack Overflow posts of 6 libraries of 4 languages. The following is one example for Stack Overflow post. And we use Twitter tokenizer to tokenize the raw data because this tokenizer can remove the code and the HTML text, but also keep the API mention structure. And after that, we manually label all these posts. And our dataset have nearly 22,000 of sentences and nearly 9,000 of API mentions and nearly 300,000 of tokens. This is architecture of our model. Our model mainly uses three different feature embeddings. Firstly, we use the global word embedding to get the word level feature embedding, and we use the char-cn to get the character level feature embedding. And we concat these two embeddings together and use the STM to get the sentence level feature embedding. And we use softmax to predict if a token is an API or not. We also use transfer learning across different library dataset. In this example, for instance, in this example, we use the NumPy post data to train an API extraction model, and we share the ways to another API extraction model, and we use the React post data to fine-tune this model to get a better performance. In the experiments, we mainly discuss 4 questions. The first question is, how well can our neural architecture learn multi-level features from input text? We conclude that with linear conditional random field for API extraction, we cannot achieve a good trade-off between easy to deploy and high performance. In contrast, our neural architecture can extract effective multi-level features from the input tests and extract The features alone can support high-quality API extraction without using any handcrafted advanced features. The second question is, what is the impact of three feature extractors on the API extraction performance? We conclude that all feature extractors are important for high-quality API extraction, and the chassis is especially useful for filtering out non-API tokens, while word embedding and bidirectional STM are especially useful for recalling API tokens. The third question is, how effective is transfer learning for adopting API extraction models across libraries of the same language? We conclude that transfer learning can effectively boost the performance of target library model with less demand on target library training data. Secondly, its effectiveness correlates more with the similarity of library functionalities and API naming characteristics than the initial quality of source library model. The last question is, how effective is transfer learning for adopting API extraction model across libraries of different languages? We conclude that software tests of different programming languages and of libraries with very different functionalities will increase the difficulty of transfer learning. But transfer learning can still effectively boost the performance of the target language model. Well, thank you for listening. If you have any questions, please feel free to email us. And thank you again.